Welcome back to Physics 152 Online. Today we're going to be defining some new quantities and preparing to be able to analyze the behavior of batteries and resistors in simple direct current circuits. So we'll begin with the definition of electric current. Electric current is related to charge, but electric current, as the name might imply, is defined as the rate of flow of charge through a particular cross-sectional area of a wire or some kind of circuit device. The direction of current is defined, and this goes back to the days of Benjamin Franklin, by the convention that the flow of positive charge is the direction of the current flow. Today we know otherwise. We know that in most metals and many other materials the flow of electric current is carried by negative charges, but we still stick with the original convention. And so here's a picture showing charges individually flowing through a cylindrical shaped wire with a cross-sectional area A. Current is simply defined as charge per unit time flowing through a particular plane in the conductor. The units of current, therefore, in the international system are coulombs per second, and we give the special name ampere to that unit. Now there's another quantity that's related to this that's often defined, and that's the current density, the current per unit area in a particular conductor. So if you know the current and you divide by the cross-sectional area, that gives you the current density J. We may occasionally have the need to refer to that. Now, what about resistance? It turns out that if you had a perfect conductor, like a piece of copper, where all of the atoms were sitting at their equilibrium positions in a perfectly ordered arrangement, and there are no impurities, that if you applied a voltage across the ends of that copper wire, the current would flow without any resistance. However, even at room temperature, the atoms don't sit motionless at certain ordered positions, but they actually vibrate because of the thermal energy of the system even at room temperature. And those vibrations cause electrons that are moving through the material to get scattered occasionally. And that scattering reduces the flow of electrons. It inhibits the flow of electrons and produces something called resistance. Defects in the crystal structure of the conductor wire can also cause resistance. So, non-metal materials can have even larger resistive effects. So the tendency of a material to resist the flow of current is called its resistance, and we define it in a way that easily can be measured experimentally like this. If you were to apply a voltage across a sample and you measure the current flowing through it, then the ratio of those two is the resistance. Of course, the unit here is volts per amp, and we give the name ohms to that, named after the German scientist of the 19th century, Georg Ohm. Now, one note about this is simply the definition of resistance. It is not in any way a statement of Ohm's law. We'll get to Ohm's law in a minute when we talk about the behavior of real materials. This just says measure the voltage, divide by the measured current, and you get the resistance. Now, what's Ohm's law? Ohm's law is a separate statement. Ohm's law says that a metal that obeys it, or any other material that obeys it, has the property that the resistance is independent of the applied voltage. So here's what you would do experimentally. You would have a particular device or wire or circuit element. You would apply lots of different voltages and measure the current for each voltage and plot that on a graph. And if that's a straight line, then the slope of that line is constant. And that's a statement that says the device behaves where the resistance does not depend on the applied voltage, because the slope of this is 1 over R. And if that slope is constant, then we can say the potential difference across the device is equal to I times R. This is Ohm's law. Notice on the second plot that here we have a device, and this actually is the kind of shape that you get for a diode that's widely used in electronic circuits, where as you apply more voltage, the current increases in a nonlinear fashion. And so the resistance of this device, measured as V divided by I, would be different at different voltages. And so as a result, this is characteristic of what's called a non-ohmic device. It does not obey Ohm's law, even though the definition of resistance is the same as it was for an ohmic device. So what does resistance depend on? Well, the value of R for a real-world wire or resistor that goes into an electronic circuit depends on what the material is made out of, but also on the size and shape of the sample. And so we can express the resistance of a wire in an equation that separates these two contributions. We can write it like this. R is the resistance in ohms that we would measure. Rho is a quantity that's called the resistivity. And that depends only on the material that the resistor is made out of and on the temperature. So you can look up the value of resistivity in a reference book, and usually they're tabulated at some common reference temperature, which is usually room temperature. Of course, L is the length of the resistor, and we're assuming here a cylindrical shape, and A is the cross-sectional area. And you can probably figure out why these proportionalities make sense. If resistance comes from scattering of electrons off of atoms, well, the longer the resistor is, the more chance there is for that to happen. And the cross-sectional area, if you think of the flow of electrons through a conductor as being a little bit like the flow of water through a pipe, the more you constrict the device or the wire, the smaller the cross-sectional area, the greater this resistance is going to be. And so this equation separates out how resistance depends on the material properties and how it depends on the size and shape of the resistor. So Rho, remember, is resistivity, and be careful because resistivity is different from resistance. What about measuring the power that's supplied either by a power supply or by a resistor? How much power is dissipated in a resistor? One of the things that you'll notice if you ever use resistors in a circuit, if you apply enough voltage across those resistors, they will actually heat up a little bit over time. And what's happening is the electrical energy that the battery or the power supply produces leads to current flowing through the resistor, and the charges that flow through the resistor will lose some energy inside the resistor because of the collisions that those charges are making inside the resistor with atoms. So it would be helpful for us to define that power. Power, remember, is energy per unit time. So the power supply or a battery is a device that does work on charges that flow inside the power supply, and what that does is it gives those charges more energy and keeps them able to flow around a circuit loop. When they encounter other circuit elements like resistors, they lose energy. And so having a battery allows for charges to flow continuously. So we can use our expression for the relationship between a change in potential energy and charge and a potential difference like this. So what we want to do is consider a tiny amount of charge, dq, acted upon by a battery with potential difference V, and du represents the energy increase. So in a time dt, if that's how much energy is being absorbed by the charge, in a time dt, we can divide both sides by dt, and we can see that the time rate of change of energy, the rate of energy increase of a charge flowing through a circuit, is equal to the potential difference that it experiences times dq dt, which is nothing more than the current. So if you have a power supply that supplies a voltage V and a current I is coming out of it, then the product of those two gives you the power. This also holds true for a resistor, but for a resistor we can take that result and use Ohm's law, if Ohm's law applies, to express the power in two slightly different ways that might be more useful if we're looking at the properties of the resistor alone. So if you substitute V equals IR into the expression for power, you get I squared R. And so if you know the current flowing through a resistor and you know the resistance, this gives you the power. Another way you can express the same thing is solve for the current in Ohm's law and plug it into the power equation, and that tells you that the power is the square of the voltage divided by the resistance. So if you know the voltage applied across a resistor, this gives you a complementary way of calculating the power dissipated in that resistor. So sometimes this phenomenon of resistor heating or power dissipation is called I squared R heating, and sometimes also Joule heating, named after James Joule. Remember that power, even though it's written down as voltage times current still has the units of joules per second. One last comment then about voltage sources. There are two different types. There are the kinds of power supplies that are commercially available. You plug them into the wall and they will give you a certain potential difference across the terminals of the power supply. And another one is a portable battery, which usually is a source of voltage that is produced by chemical reactions that go on inside the battery. The old name for what a power supply does is to say that it is a source of electromotive force. And that's just an old way of saying that power supplies produce a force on charges that causes them to move and that causes them to increase their potential energy. So EMF stands for electromotive force, and let's just look at two different types of EMF. First, there's the ideal battery or power supply, where EMF, which has the same units as voltage, an EMF is produced inside, and it's ideal in the sense that whether we measure the voltage across these terminals when the battery's all by itself, or whether we connect this to a circuit and then measure the voltage that we have in both cases would be the same. It's the same whether current flows or not. However, in a real battery, and this is more realistic, real batteries have material inside them, and the charges that create a current have to flow through that device. And there's usually some small amount of resistance, and that's why we use lowercase r here, because it's usually a fairly small amount. And so a real battery is an ideal voltage source with a very small internal resistance in series with it. And so what does that mean? That means that if we were to measure the voltage across this device in what's called open circuit conditions, where there's no current flowing, the voltage would just be epsilon, just like it is for an ideal battery. However, if current flows through it, then the voltage produced by what's inside the dotted line is a little bit less, because a current flowing through a resistor R produces a change in electric potential. So across the terminals of this device, the voltage would be epsilon minus I times R if there's a current flowing. Of course, if there's no current, then V and epsilon are the same. So that's the difference. And if you have a homework problem where they specify an internal resistance, of course you need to take that into account. If you've got a homework problem where they just say an ideal source of voltage V, then you don't have to worry about internal resistance. So read carefully the kinds of problems that you have to see whether or not you need to take into account internal resistance. But in real-world batteries, it's there and we have to account for it. All right, next time we'll look at combinations of resistors and the analysis of simple DC circuits.